Okay, so this is the second part of the lecture today, and we will start with recalling, if you've seen this quaint but very pedagogical video of Professor Rouse, a very distinguished fluid mechanician and professor, then you will have seen him presenting to you the three basic dimensions in mechanics. But we will recall this because it is very important. They are length, time, and either mass or force. Those are the three basic dimensions. In thermodynamics, we introduce another one, which is the temperature. And in thermodynamics, then we have sometimes to deal with a little bit of thermodynamics for fluid mechanics as well. The SI units are meter, second, and kilogram. And then there are what we call the derived units. And these derived units are, for example, force. Well, what is force? Force is equal to mass times acceleration. So we can derive, as the title says, those units. And force, mass times acceleration, so 1 kilogram of mass going at an acceleration of 1 meter per second squared is what we call a unit of force, which is the Newton. Another very important quantity for mechanical engineers is work. Work is force multiplied by a distance, and so in SI units it'll be 1 Newton multiplied by 1 meter, and that is equal to the unit of work, which is the joule. 1 joule is equal to 1 Newton meter. Then we have another extremely important quantity for mechanical engineers, power. Power is equal to work done in a unit time, and so we can derive the units again, and it's going to be 1 joule of work done in 1 second is what we call a watt. These are the most important derived units: the Newton, the joule, and the watt. And you will find in most of your books, any book that you use, and particularly the one we've chosen for this class, has conversion tables in the back, in the appendix, and the back cover, and so on. There are also conversion tables online that you can find, print out, and so on. And I have placed a couple of links on Blackboard to some that I have found are more useful or less annoying because they have less advertisements or something like that, you know. And there's also a link, I believe, to the National Institute of Standards, and with some useful conversion factors, and also the prefixes that determine magnitude. For example, kilogram, the kilo prefix means 10 to the 3. Micro, and so on. All of those prefixes indicate a decimal, a power of 10 that you append to the number that goes with the unit. Okay, so the next thing we need to do is recall the measures of mass and weight. And just to be on the same page for this course, we define the density, you know, but let's just make sure that we have this mass per unit volume. The dimensions then are going to be mass divided by length cube, and SI units are therefore kilogram divided by meter cube. And in terms of fluid mechanics, an important insight to have is how density changes with temperature or pressure. And the density of liquids changes very little, in fact. With temperature and pressure. For example, some example values that we can cite, and values that you need to sort of get used to by doing several exercises. Some of the numbers you should be able to inspect and sort of have a feel for. For example, the density of water. You know, if you look at, say, a box of juice that has 1 liter, you kind of know how much that weighs. How much is it? 1 liter of water. A kilogram, excellent. 1 kilogram. And so if you have 1 meter by 1 meter by 1 meter, a very large cube of water, how much do you think that weighs? Who said? Yes, 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 very good. 1,000 kilograms, excellent. 1,000 kilograms. So that is the density of water, 1,000 kilograms per cubic meter. That is water at, say, 4 degrees Celsius. The density does change a little bit, but not much, is 1,000 kilograms per cubic meter. If you look at water at 15 degrees Celsius, then, as I said, it changes very little, and it is actually 999 kilograms per cubic meter. Gasoline at 15 degrees Celsius. What do you think it is, gasoline? Is it lighter or heavier than water? It's lighter. It floats. If you have a layer of gasoline on a puddle, it'll float, right? How much? More or less, you have an idea? The density? How much more, how much less than water, do you think? Take a guess. 3/4. That's a very good guess. It's about, yeah, it's about that. To be precise, it really is 68%. So that's very, very good guess. 680 kilograms per cubic meter. Yeah, it had to be less than 1 and more than a half, right? So very good guess. That's a very important thing to develop as engineers. This kind of thing that you have, that you know, just take the painter's look at something with a distance and you get a feel for the magnitude of things. From certain insight, from doing exercises over and over again, you get that. You have an idea of things that should, so then when you develop that, if you're doing a very terrible mistake in a problem, you will get to the answer and you say, no, that doesn't make sense. It can't be that this thing weighs a ton. It just doesn't make sense, right? So with experience, you need to develop that, where you sort of know things by, you can imagine the size and sort of weight and density, and that you develop insight. That is why it is important to do practice with exercises and homework and things like that. It's not to just exert our authority over you. It's just because actually over time you do develop a certain feel for things if you use them a lot. And values, the certain values of density and viscosity and so on for the fluids is one of those things that you need to become acquainted with, okay, magnitudes and things like that. So what do you think about seawater compared to just water, normal water? What do you think? Denser, right? It needs to be a little heavier. How much do you think? Very good. It's not very much heavier, but it is actually 1030. So here's a good engineer in the making with some very good sense for dimensions. Okay, that's what we develop over time. Okay. Now here's an interesting thing about water. Water is really a very, very quirky material, fluid. It has this very strange behavior that if you look at the maximum density of water, it happens at about 4 degrees, this is the temperature here in degrees Celsius. My plot here is a little bit sloppy and it doesn't have labels. Very important to put labels in your plots. So here I'm teaching by a counter example. My plot is bad because there are no labels. And here we have the density. So at least it says density as a function of temperature, so I'm giving you a hint there. And the units, very important. So here's the density. So the maximum density occurs at a temperature of 4 degrees Celsius. Now that's very interesting for water because it means that between freezing and 4, the water gets less and less dense as it goes towards freezing. And so colder water down here is less dense, so it rises. And warmer water in this range is more dense, so it sinks. And this is a very important thing for the planet Earth because it means that ice floats. And because ice floats, there is, through the ages, incredible things that have happened and life has been able to survive thanks to this. Because ice will just form this layer on top and the water underneath is not frozen and life can continue despite being in the Arctic or being a glacial age and so on. It's a very important feature of water. And of course on the other side we have the opposite thing. We have on the other range of temperatures we have that warm water rises in here and cold water sinks. That is in the other range above 4 degrees Celsius. Okay? Oops, not that one, this one, shift 5. Okay, so a couple more things that I'm going to have a few definitions here just to close this part that we need to introduce and make sure that everybody is clear with. One is specific volume. Specific volume, we use this a lot in thermodynamics as well, is volume per unit mass. And therefore, it is simply 1 over rho, the density. Specific weight, we use the Greek letter gamma, is weight per unit volume. And so mass per unit volume is density, and to get weight, we need to multiply by an acceleration, in this case, the acceleration of gravity. So the units, yes? The symbol? Gamma. Is my gamma. So you not only need to understand my handwriting in English, you also need to understand my handwriting Greek on this graphic tablet. So bear with me. Okay. Units for specific weight are Newton divided by cubic meters. And for example, let me just see that where I have the space for that. Water at standard conditions, 15 degrees Celsius and so on, has a specific gravity of 9.8 kilonewton divided by cubic meter. Specific gravity, we use just the letters SG for that, is the ratio of density of a fluid to the density of water. But this at a specified temperature. So for example, so we write rho of the fluid, whatever fluid it is, divided by rho of water, and usually with the temperature could be at 4 degrees Celsius, but this needs to be specified. It could be a different, you know, it will change with temperature. Again, a reminder, and some of you are taking thermodynamics concurrently with fluid mechanics, so let's make sure that you remember your ideal gas law. So remember, gases are highly compressible. Liquids, in the contrary, are not. For gases, we have the ideal gas law. Rho is equal to P divided by RT, where P is the pressure and R is the gas constant, which you will find in tables of thermodynamic properties, usually in the back of your fluids book, thermo book. Those will be available. The pressure, let's define the pressure, is a normal force per unit area on any plane. The dimensions of pressure are therefore force length to the minus 2. The same as stress, force per unit area. You see there, okay. So the SI units for pressure and the same for stress are Newton per, divided by meters squared, which has a name. We call it the Pascal. 1 Newton per square meter is equal to 1 Pascal. In British units, of course, we use PSI, which is pounds per square inch. And again, those conversion factors, you need to sometimes have them available. And as you do some exercises for your homework and so on, and additional exercises that you do for your own fun as well, then you should sort of accumulate a few, maybe in an index card, a few of the ones that you use the most, because they will appear over and over. And PSI to Pascal is one that appears very often. Absolute pressure is the pressure measured relative to absolute zero or perfect vacuum. So I forgot one here in my list, which is the definition of a standard sea level atmospheric pressure, and that is in Pascal 101.33 kilopascal, or in PSI it's 14.696, that is PSI. These are the type of numbers that you also need to get sort of really acquainted with. So you see something that says 100 kilopascal, and you need to sort of get an idea, oh, that's just like 1 atmosphere. 15 sort of PSI, oh, it's kind of like 1 atmosphere. So you know that if you look at the number and it says 1 kilopascal, you say, well, that's very small compared to atmosphere. And you might think, well, that's kind of, so it doesn't make sense in the context of the problem I'm looking at. Or it says perhaps 100 Pascal with no kilo in front, and you might think yourself, wait a minute, this is supposed to be about atmospheric pressure, so surely I have forgotten my kilo prefix somewhere, and you go back and look because you have a feel for what 1 atmosphere should be. Okay? Okay, so with respect to atmosphere, again, we measure pressure, and it's called gauge pressure. And the important thing, it is you have to be very careful not to mix this two. In a problem, you might have, it might not say whether it's gauge or absolute, and you might have to realize from the context which one it really is, relative to atmospheric pressure or absolute. Okay, something to look out for to not make mistakes. And the reason we use gauge pressure, and the word gauge should sort of be a hint, is because the ways that we measure pressure many times have to do, for example, you have a device that is connected to a tank which has a gas inside. The device that measures the pressure really has the pressure of the gas inside the tank on one side and the atmospheric pressure on the other side, and the mechanical device is able to determine the difference between the two, and that gives you a reading on a gauge. So the historical ways that engineers have been able to measure pressure result in the fact that we often have to deal with a relative value rather than absolute with respect to a perfect vacuum. Okay? So I'm giving you some tips as we go along, which I'm going to be more precise now. Today is your first class, so I know you're very concerned of doing well on your courses, and one of the big parts of doing well in the course, one of the big parts of the assessment is your exam. So some tips about how to do better in exams. One of the first tips that I can give you is to train yourself to carry all units explicitly through every calculation. Believe me, this is not being pedantic in any way. It really is extremely useful to do this, not only in homework, but throughout your career as engineers. You will learn that you never want to stop doing this. Carry your units explicitly all the way through, meticulously. It is extremely important. I really can't emphasize enough. So let's do an example. This is so my first example. And For these examples that I'm going to do now, I have them written out, so you don't have to actually write down all of the problem description, because I've copied this over on a nice typed page and made a PDF, and I'm going to put it on Blackboard. Okay, so let me just read it to you. So I'll make a diagram as I read it, so that you can take notes of what the problem is, and then you can have that additional PDF for your information. So consider two parallel plates. So we have two parallel plates which are separated by a distance of 2 millimeters. And there's some fluid in between. Okay? The upper plate is pulled at a velocity, like we've shown before, and the velocity u is equal to 1 meter per second. And then a shearing stress is measured on the surface of contact with the fluid. So shearing stress with some sort of device that gives us the force we measure to be 150 Pascal. So is that compared to atmospheric pressure, is that value big or small? Quite much smaller, right? How many times? Like 1,000 times smaller, right? Or, you know, a little bit less because it's 150 instead of 100, right? Yeah, it makes sense. We're just measuring the friction, the shearing stress due to some sort of friction, so that makes sense. Okay, it doesn't. If it was a whole atmosphere, that would be a big number. Okay, so it makes sense. So now the question is, find the viscosity of the fluid. So, what is the solution to this example? Well, we know that the relationship, we assume here nobody's telling us anything about the fluid, and so we're going to assume that it's a Newtonian fluid because they're not telling us that this is anything strange. So we assume that there are usual linear relationship between the stress and the strain, and so we write tau is equal to mu du dy. And in this case, we have a linear relationship that goes from 0. The velocity of the fluid goes from 0. This is stationary over here. The velocity at the top is u, so it goes from 0 to u. Each layer of fluid then will have a velocity like this that goes from 0 to u. Remember, the fluid, there's a no-slip condition, so the fluid sticks at the wall. So if the wall at the bottom has 0 velocity, the first layer of fluid has 0 velocity. The top wall is moving at velocity u, so the layer right next to it is moving at the same velocity, u. So the fluid in between has to adjust from 0 to capital U. So here we have this linear relationship, and therefore we can pretty well estimate the gradient of velocity here, and it's equal to the velocity u divided by, well, I called it d. Let me just use the b so that I'm consistent. Okay. So now we can very simply solve for the velocity, for the viscosity. And we write tau divided by u over b. So now we can use our data that we were given, but I remember to put all of my units in, and I'm going to carry them all the way through. So I have 150 Pascal. What's Pascal? Well, Pascal is Newton divided by meter squared. So I'm going to write all my units there. And then I have velocity, which is 1 meter per second, divided by b. b is given in millimeters, 2 millimeters. So maybe I can immediately make a conversion in my head because I see that I'm going to need meters. And I'm going to be able to write immediately here without doing the millimeters. I'm just going to write in meters because I can see that that's what I'm going to need. So 2 millimeters is 0.002 in meters. But I write my units explicitly. This is my tip to do better in exams. I'm serious. It really makes a difference. You will get better grades if you follow this tip. And now I can put these numbers in my computer and write the number here, in my calculator. And before I finish my problem, I check that the units do give me the result that I'm expecting. So here I have this meter over here. So I have 1 over meter squared. Obviously the Newton remains because it's only 1 Newton and no other Newtons. Obviously, this second that is down here goes to the top, right? And what happens to the meters? Well, this one and this one cancel out, so this one is the only one that remains, meters squared. So I look at that and I think, does it make sense? Are those the units of viscosity? Yes, they are. Then we're content, and now your problem is finished. You've carried out all your units and checked that they make sense. If there's a unit that doesn't make sense here, you will know that you've made a mistake somewhere in the algebra of your problem, and you can go back and look for it. Okay? Second example. Let's do another example. So this is example 1A. And example 1B is the following. We have a layer of water that flows down an inclined plate. A layer of water flows down an inclined plane, and we are able to observe by some means that there is a parabolic velocity profile. Velocity profile. So it's given, or it's a product of the observation, that u divided by some sort of a reference velocity here in this problem is equal to 2y divided by h. H is the height of this layer of fluid minus y squared divided by h squared. And we're told that our reference velocity is 2 meters per second and the h is equal to 0.1 meters. So this is the situation. We have a parabolic velocity profile on a layer of fluid that is coming down as inclined plate. And the question is to find the magnitude and the direction of the shearing stress. Okay, so again, we have our Newtonian relationship. Tau is equal to mu times du dy. Now we are given a velocity profile, so we have to obtain du dy from that velocity profile. So for this case, du dy is equal to, let me multiply by capital U both sides of the equation and then take the derivatives. So we have u here, and the first term, when I take derivative with respect to y, I just have 2 over h. For the second term, I have, well, I take the derivative of that, so I have 2y divided by h squared. Here's my derivative. And you want to find out the shear stress where? Well, at the wall. That's where the friction is happening, right? The friction with respect, that's what we want to calculate. The magnitude of the direction of shear stress at the wall, at the plate. So that is for our problem, the origin of the coordinate system. And we want to find tau at y equals 0. So we evaluate du dy at y equals 0. And, well, we see we just get U, capital U, times, well, let me write the 2 here, it's prettier, and divided by H. And so now we can calculate tau is equal to mu times du dy. And I have all the data. I go in a table, and this I'm skipping some things. It was a layer of water, so we go on a table and we get the mu value of water, and it is equal to 1.12 times 10 to the minus 3 Newton second divided by square meter. This would be a value that would be available from a table. So now I can put that in, and I put the number 1.12 times 10 to the minus 3 and the units, and I carry my units all the way through, Newton second divided by meters squared, times 2, and the velocity is 2 meters per second, divided by h, which is, what was it, 0.1 meters. So all my units are there, and I can check that the result is what I'm expecting. I put those numbers in the calculator, and I get 4.48 times 10 to the minus 2. But the important thing is to check the units. This meter goes away with this meter. This second goes away with that second. Let's be explicit here. This second here cancels. I can cancel my units like that. This second goes away with that second. This meter goes away with this meter, and I'm left with Newton divided by square meter. Are those the units of shear stress? Yes. Therefore, we are pleased with that result. We're confident now. Okay? If it wasn't, we go back. We know that we have a problem. We've made a mistake. We will go back and check. So remember, a few points to remember. You can never add or subtract terms that have different dimensions if the equation is valid. So, as an example, you can't add dollars and kilograms. If you're getting something in the store, you can't add dollars and kilograms, right? It's just not compatible. In an equation that makes sense, the dimensions have to be the same. You can add or subtract terms that have the same dimension but different units if you make the appropriate conversion. For example, you can add, if you're making a budget for a trip, you can add dollars and euros if you make the conversion from euros to dollars first before adding, or from dollars to euros. They're the same dimension, the dimensions of currency in this case. Okay? And finally, the units are an integral part of a dimensional quantity. That's why it's very important to carry your units always in the calculations. Another point on how to do better with exams. When using the ideal gas law, always use absolute temperature and pressure. Always absolute temperature and pressure. So make sure you check if you have a problem and you're giving a temperature, that you convert that to absolute values. You're given a pressure, you ask yourself, is this absolute or relative? And if it's not, you need to convert to absolute before you plug it in your equation, okay? For example, consider nitrogen. And we say that it's compressed to 400 kilopascal in a tank, and it reaches a density of 4 kilograms per cubic meter. And you're asked to calculate the temperature in degrees Celsius. So we use our ideal gas law. And so, P is equal to rho RT. So we are asked for the temperature. We solve for the temperature is equal to P divided by rho R. And for the values that we have here, T is equal to 400 kilopascal divided by, we're given density is 4 kilograms divided by cubic meter. Notice I carry all my units multiplied by R. I have to look up the value of R in a table, and I obtain, and I'm going to take out the kilo unit here by writing explicitly 10 to the 3. So I no longer have that kilo prefix, and I write my Pascal units in terms that I can simplify them with the other units. So it's Newton divided by square meter. And in the denominator, I still have 4 kilograms divided by cubic meter. And I've obtained from some table the value of R for nitrogen, 296.8 joule divided by kilogram degree Kelvin. So I put all of that in my calculator and I check my units and I obtain 337 Kelvin. So now I'm asked for the temperature in degrees Celsius, and so the temperature that I'm asked in degrees Celsius is equal to the temperature in Kelvin minus absolute zero, 273.15. I just write 273, and that is equal to 64 degrees Celsius. Always use absolute temperature and pressure in your ideal gas law or any equation of state. And one more example of this. Oh no, another rule, another tip on how to do better exams, and another example to go with it. This other tip is to use the grid method for complicated unit conversions. How is that? So for example, we have this following problem. We're asked to estimate the power required to ride a bicycle if the speed that we're going to ride is equal to 20 miles per hour, and we are told that the required force to move against the wind speed, so the drag force of the wind is equal to 4 pounds force. But you're asked to estimate the power in SI units. So you want the power in what units should it be? Watts. Very good. So we want to get the units in SI. So what's power? Power is force times velocity. And so what we have here is, so we're going to write with the grid method, because we don't want to make any mistake here. It's a little bit more complicated, and so we go. P is equal to 4 pounds force times 20 miles per hour, and I use now the conversion between miles per hour and meters per second. So write 1 meter per second is equal to 2.237 miles per hour. I have that in my little index cards or material that I have prepared for my exam. Then I want to convert from pounds force to Newton, and so I look at my conversion between Newton and pound force, and I know that 1 Newton is equal to 0.2248 pound force. Now I check that my units cancel like they should, and I see that miles per hour is here, miles per hour here, it's here, it cancels out. Pounds for is here, pounds for is here, it cancels out. I'm left with Newton and meters per second, which is what I want for watt. And now I'm happy that I can just multiply and divide the numbers that are left here. I have 4 times 20 times 1 divided by 2.237 times 1 divided by 0.2248. I can put all those numbers in the calculator. It's all very nice and tidy, and I obtained my result is 159 Newton meter divided by second, which is the same as 159 watt, which is what we were asked to obtain. Very simple tip that will help you quite a lot to solve problems and not make mistakes. It is truly a way to do better in exams. And so to finish, first, just to mention the advantage of the international system of unit. In the current marketplace, which is the current reality of a global market in a global world, you have to admit that it's a dominant system of measure. In fact, I believe there are only 2 countries that haven't really adopted as a norm, or 3 maybe. I think it's 2, Liberia and the US, something like that. If there's a third, there's another small country somewhere over there. And so really, the whole world uses this, okay? It's very straightforward with the SI units to use large or small numbers because of the decimal system, and you have all these prefixes to do micro, nano, then you have kilo and mega and so on. So you can very easily work with large and small numbers because of that, the standard prefixes. So before we go, just a couple of, I'm going to end with a couple of stories today of 2 very large stories of unit mix-ups. One is the story of the Gimli glider, and I have a link on Blackboard for you to read a story about that. So this is in, I think, 1983 or something, that a Air Canada flight from Montreal took off on the freshly out of the 4-month new Boeing 767, and the pilots realized that they got their information about the situation of the flight of the plane, and the fuel gauges were not functioning. So when the fuel gauges are not functioning, the captain has the option of make a decision of going or no going. He decided to not cancel the flight, and instead he instructed the ground crew to measure the fuel that they were loading into the fuel tanks with what's called a dipstick. Just a stick that has some gradations, and they measure. And they had 3 different teams independently measure with the sticks the amount of fuel, and everybody was content that they had the amount of fuel that they needed. The plane takes off, and a couple of hours later, there's some light that turns on. There's a problem with the fuel pump. Captain and the co-pilot discuss these things and what is going on. A problem with the fuel pump. They try to change to the other pump. It seems things are all right. A little while later, another light goes off. The other fuel pump goes off. They're reading the flight manual, looking for operations, what to do if both fuel pumps are failing and they don't know what's going on. One engine goes off, and they're like, calling the tower and looking for an alternative place to land because the one engine went off, and they don't understand what's going on. Our fuel pump is broken. They have no idea what's going on. A little while later, the whole story is a very long story of quite actually amusing details of the cockpit conversation going on in this account of this event. The tower asks the pilot whether they're going to need assistance, meaning, do you need the fire brigade, right? Assistance, it's a euphemism. They say, no, we're fine. We're going to land in, say, Winnipeg. A little while later, the other engine goes off. Suddenly, there are no engines of 767, okay? This is not a plane that normally glides. To make a long story short, they had to decide to go to this little side airfield that was not on operation for commercial flights. It so happened that this doesn't have a tower. When the 2 engines go off, a commercial jet aircraft does not have any controls, because all the controls are by hydraulic power. So you don't have engines. So what they have is a little sort of like a turbine that pops out from the belly of the plane to use the wind to drive some emergency pumps to get hydraulic power to get some controls. Otherwise, you don't have, ailerons. There's no controls. So the speed of just the glide is able to provide the minimum amount of hydraulic power for the and the batteries allow you to keep the radio running, and that's it. And you have no instruments, nothing, except perhaps for the the compass and the couple of instruments that indicate altitude that just function by pressures and are not electronic, just a couple of basic instruments. And so they go, and basically they had to glide to this airfield, and as they approach to land, obviously they have to slow down to land, and as they slow down, they're losing the power that is generated by this little turbine, and the pilot has to do the last bit of maneuver by sheer force. Imagine a 767, and you're out of hydraulic power, and you have to use muscle to move the ailerons, okay? It's really, and all the control surfaces is unimaginable. Finally, they were able to land without loss of life. The plane suffered some damage. There was other aspects of the story, like there were some people barbecuing and in the airfield and so on. And in the end, it was a happy ending. But in the investigation, they found out the whole origin of the problem. Of course, the plane had run out of fuel. The reason it ran out of fuel is that this brand new plane coming out of Boeing was all in metric system. Their operations that they have are manual. The operations of the company were still in British. And so when they calculated the amount of fuel to put on the fuel tanks, they used some sort of unit conversion between liters and the mass, because the pilots need to calculate the mass of the plane to make sure that they're within the weight that they can carry. And instead of obtaining a certain number of kilograms, they were obtaining a certain number of pounds. They ended up with half the fuel that they needed. And of course, they ran out of fuel. So a unit conversion that in this case put in danger the lives of 70 people. The other case is the Mars Climate Orbiter. And here, a navigation error of a NASA subcontractor caused the orbiter to enter a very low orbit, and of course the spacecraft was destroyed by the effects of the friction of the much denser atmosphere at this lower orbit. This was a mix-up between imperial and metric units, again, between the different teams working in this. The cost, $327 million. Disappeared, burned in air because of a unit mix-up. So the take-home message is that as engineers, this meticulous attention to the units is of paramount importance to both safety and the management of costs.